In this video, I introduce end-to-end federated learning for autonomous driving. Federated learning is the edge-distributed computing technique, which is used to accelerate training of a driving model without sharing a user's private data. Each edge vehicle copies the model from the aggregation server and then trains the model locally using the local training dataset, and then sends the local trained model parameters to the aggregation server. The aggregation server updates the global model using the locally trained parameters. The advantage of asynchronous federated learning is that we don't need to synchronize the local training procedure. Here is the architecture of end-to-end federated learning model, which includes two convolutional neural networks. One is upper, one is lower, one fully collected network. The upper convolutional neural network uses three consecutive frames as an input to extract the spatial local lower dimensional features. And the lower convolutional neural network uses two consecutive optical flow image as an input to extract the temporal lower dimensional features. We concatenate them together to be one low dimensional features. And then we use this low dimensional features as input to the fully collected network to predict the theory angle value. Here, the convolutional neural network uses the exponential linear unit as a nonlinear activation function. And the fully collected network uses the ReLU as a nonlinear activity function. We use prediction and the ground truth to define a loss function to train this local model. Let's see the detail inside each local model. We got the images from onboard camera and then feed to this training window. We got the new image from the camera and we discuss the old images. And then that means we throw the old images away. And then from this the images in the training window, we got this optical flow frames and the image flow frames. We use them as the input to the convolutional neural network, and then I use this corresponding label to define the loss function to train this model. And then we communicate with this aggregation server, and then to use this aggregation server to communicate with the other vehicles. Here, let's see more detail about the update in the federated learning model. For example, this vehicle K. First, before we update the model, use the local training dataset, we first need to check the model is if the model is out of date. If out of date, that means this model has at least 6 version difference from the global model. That means we need to copy the model from aggregation server to this local server. And then we use the local training dataset to update to train the model locally. And then we send this locally trained parameters to the aggregation server. And the aggregation server uses this locally trained parameters to update the global model parameters. Here is the learning rate. And use this asynchronous federated learning. We don't need to synchronize the local training procedure. That means we cannot train local model independently and communicate only with the aggregation server. And then now we send the contribution from the local training data set to the global model. And finally, we got the convergence global model. And then now all the edge vehicles can share the results from the global model. And that means we can gather a very good autonomous driving model. For more details, please check with this reference. Thank you.